Okay, prayer. Yeah.
Okay, as you all know, my name is Jeremy Eckenrode, and the presentation I am doing is the batch distillation. Brief outline. Basically, I'm going to discuss the theory of the batch distillation in general, some factors affecting the distillation operation, the operation of the distillation, and also some advantages of the batch distillation. Then I'm going to discuss the data that I received from the experiment, and also the results, and then wrap it up with a conclusion. The batch distillation is basically a type of distillation where there's a fixed amount of charge that's added at the beginning. The distillate composition varies with time, and the bottom product composition depends on the number of trays and the reflux ratio. Since the composition changes with time, the process is obviously not in steady state. So basically, prior to starting the process, the top distillate has a higher concentration of the more volatile substance. In this case, it was methanol. But as time passes, the top distillate becomes lower in concentration, or the methanol has a lower concentration. Concentration. Some factors affecting the distillation operation are, the first one's reflux conditions. As the reflux ratio is increased, more and more liquid that is rich in the volatile components are being recycled. The volatile components in this case, like I said, is methanol. They're being recycled back into the column, which causes better separation. Also, some adverse vapor flow conditions can cause foaming, entrainment, weeping, and flooding. Basically, foaming refers to the expansion of liquid due to the passage of vapor. Excessive foaming may cause the foam to mix with the liquid onto the tray positioned above it. Entrainment refers to the liquid carried by the vapor up to the tray above, which is caused by higher vapor rates. And then excessive entrainment can cause flooding. Flooding is similar to entrainment in that it's brought about by excessive vapor flow, causing the liquid to be carried up to the tray above. However, it differs in the fact that the excessive vapor also backs up the liquid in the downcomer, causing an increase in the liquid on the plate above it. Weeping, on the other hand, is caused by low vapor flow rates, or vapor flow rates, which is caused by the pressure, not enough pressure to hold up the liquid onto the tray. Some advantage of batch distillation: relatively small amounts of product are used, so it's pretty cost effective. Also, different distillations can be done using the same equipment. There's no continuous feed like in a CSTR. Therefore, basically the pot is charged with liquid and could be drained at the end of each run. Also, the distillate can be withdrawn continuously or collected, as we did in our case, in the accumulator. In the refractive index, which we used a refractometer to measure the refractive index. It's basically just the ratio of the speed of light in one medium compared to that in another. In the first week, we made our reflux ratio equal to infinity. And the distillation column was set to operate at total flux, which, like I said, was infinity, the reflux ratio. And then once a general bubbling occurred, the power was gradually turned down until we obtained the weeping point. At this point, the pressure drop as well as the boil-up rates were recorded at each increase in power. After the weeping subsided, the power was slowly increased to the point at which the flooding was achieved. And in between every 40 minutes or 20 minutes, we measured the boil up rates as well as the pressure drops. This table basically just, it's not all the data, it just shows the weeping and the flooding, where the weeping started or ended, and then the flooding, where the flooding started, at what power and the boil up rates. There's a large discrepancy. At 850 watts and 950 watts, we have very different pressure drops, one at 0.7 and one at 0.14. I'm really not exactly sure what could cause that. Besides, I mean, unless we ran another experiment, there really isn't a way to determine what's happening in there. So, due to that discrepancy, there really wasn't a way to find a trend. It should basically, here's our weeping points are in red, and then the flooding points are in purple. It basically should go kind of linear and then rise up and then become almost linear again. But in our case, it's really jumping all over the place. And then the second week, our reflux ratio was 1:1, which means that for every part of the reflux that goes down the distillation column, one part is collected as the distillate. And then, like I said, every 20 minutes the volume was taken in order to determine the boil up rate, as was done before. And then a sample of the distillate product and a sample of the bottom reservoir was collected and placed onto the refractometer in order to measure the refractive index. All right, this graph is how we determine the mole percentage of methanol from our experimental refractive indices. Basically, it's real simple. We found our refractive index and found the point, basically drew a straight line over, and then really came the tricky part of determining which side of the graph we use, since we'll have 2 points basically. Now with basically without doing another experiment, maybe adding water to the liquid and determining which way the refractive index changes, we're basically making an assumption that the weeping point should, we basically used it was supposed to be 8 liters of DI water and 2 liters of methanol to begin with, which I'm not exactly sure that was the case. It's basically about 25%. So from the 25% line, when it's weeping, we're assuming that the methanol is decreasing, and with the flooding, it's increasing. So we use that part of the graph for each one. So basically, like I said, when determining the mole percentage of the distillate product, the larger mole percentage of methanol were used, which was the right side of the graph, and because it contained more methanol than water. And then when determining the mole percentages of the bottom reservoir, we use the left side of the graph, which is the smaller percentages of methanol. And then this is the graph of our refractive indices, or the percentage of methanol versus time. And as expected, the mole percentage of the methanol decreases with time. However, the bottom reservoir should increase with time, but it stays relatively constant. And then basically in conclusion, I described the batch distillation and the factors affecting it, as well as the advantages of it. once again, the factors affecting the distillation condition are foaming, flooding, leaping, possibly entrainment, and then basically just the data and the results. Any questions? Derek?
So when you were during the first week of your boil rate, when you opened up the valve, did you let